Welcome everyone. Welcome to AIC session on Stencil Computing webinar series. My name is Quinn Chen. I'm serving as a program chair-elect of the section on Stencil Computing. I'm also an associate professor in statistics at the University of Connecticut. Today, I'm very glad to serve as the moderator for this talk. Before I get started, I want to just say that our committee on this webinar series consists of our current section chair, Dr. Jing Yan, our past chair, Dr. Usha Govendra Juno, our chair-elect Mina Santikia Rondell, and our program chair Lin Long Kong, and our Council of Section representative Dr. Hua Zhou. They worked hard to put this together. Now let me introduce our speaker today, Dr. Chris Rackauckas. Chris is the Director of Scientific Research and Pumas AI, the Director of Modeling and Simulation at Julia Computing, co-PI of the Julia Lab at MIT, and the lead developer of the Scientific Machine Learning open source software organization. He is the lead developer of the Pumas project and has received the top presentation award at every ACOP, American Conference on Pharmacometrics. In the past 3 years, for improving methods for uncertainty quantification, automated GPU acceleration of nonlinear mixed effects modeling, and machine learning assisted construction of NLME methods with deep NLME. So for these achievements, Chris received an Emerging Scientist Award from ISOP, International Society of Pharmacometrics. For his work in mechanistic machine learning, his work is credited for the 15,000 times acceleration of NASA launching series simulations, and recently demonstrated a 60 to 570 times acceleration over Modelica tools in HVAC simulation, and earning Chris the US Air Force Artificial Intelligence Accelerator Scientific Excellence Award. So we are very glad to have Chris here. Today, Chris is going to talk about accurate and efficient physics-informed learning through differentiable simulation. Let's welcome Chris.
Yeah, thank you very much. Yeah, so what I wanted to go through today is really, this kind of general topic of scientific machine learning. What is scientific machine learning? And then what are some of the tools and methods and the mathematics behind how it's working to kind of show where the discipline is at and what are some directions that people are going next. And I also want to highlight a lot of what are open questions, right? So a lot of what will be shown today is, the computing and the empirical results that we've gotten on the method so far. And I know that, some things will be like, well, can we prove how good some of these methods are? And, can we prove some ideas of information in models? And at this point, we can't prove all of that. And I think that makes it more interesting anyways. And so I really want to show, these are the things that we can be doing. These are the things that we've done now, and this is where we can go in the future. So, what is scientific machine learning? First of all, right? Scientific machine learning is model-based, data-efficient machine learning, and so you can think about it as the idea of traditional data science or machine learning is all about how do I take a model or how do I just take a clump of data and how do I get the best prediction from that, right? Now, people who do mechanistic modeling, like physical models or biochemical models, right, they generally have ordinary differential equations, Gillespie simulations, or agent-based models that kind of capture their system, right? And what we're doing with scientific machine learning is that we're using the mixture of these two, right? So it's neither all data-based, nor is it all predictions from a model, but it's neural networks inside of models that are giving certain missing elements to the model. And I'll describe exactly what I mean with some concrete cases in a sec here. But one of the real questions that's really getting involved these days, right, especially for someone who does scientific computing, is how can knowledge of numerical analysis also help out what we're doing in this space of models plus data plus numerics? And what I'll show today is that really using some of the ideas that we have from numerical analysis seems to greatly improve some of the methods that we have. So it's not something where you can kind of just take a recurrent neural network and say, let's throw this on an agent-based model, right? The things that we do to improve convergence rates actually help out machine learning, and we can bring all this together. So a general outline of this talk is I'm going to start by talking about a lot of the scientific machine learning applications, some of the results we've seen, some of the results our collaborators or people who have used our software have seen, to really kind of build a space of what is going on, what are the things that are useful, right? And once we have established that idea, I want to go into the software itself and start looking at what are some of the mathematical questions and what are some of the mathematical problems that we've been solving in order to get these kinds of results. So the core of it, and where a lot of these methods stem from, is this thing that's called a universal differential equation. It's, just the very, if you just read the name out loud, you get exactly what it is. It's universal approximators with differential equations. So what is a universal approximator? It is some kind of parameterized object that can approximate any Rn to Rm function. Neural networks are one example of this, though we don't use neural networks in all the cases. We also, things like Fourier series, Chebyshev series, etc., can be used appropriately as well. But the reason why you see neural networks all over the place is because they're a generally useful universal approximator in the sense that for very large dimensional cases, they tend to do very well with compute. In small dimensional cases, Fourier series and Chebyshev and everything is much more has better convergence and everything. But when you get to the very high dimensional cases, when we say high dimension is like more than 8 dimension, neural networks tend to have good properties at that range. So what does a UDE look like? So we have something that can capture functions, right? Something that can act like any Rn to Rm function. What do we do with that, and how do we mix that with the model? So here I just have a quick example of, let's say we're looking at a system and we look at rabbits and we're just like, okay, rabbits, if you leave them alone, you tend to just get exponential growth in the number of rabbits. And if you have your wolves and you leave them alone, you tend to get exponential decay in the number of wolves, right? And so there's our model. This is what we know about the model. We know that these two pieces it's true in some sense, right? We know, but what we don't know is the rest of the model, everything else, right? We don't know if you stick a rabbit and a wolf together. Well, let's say we haven't done that before. We don't know what's going to happen, right? So there's some interaction that happens between these terms. And if we knew the mechanism, we would write down a differential equation that describes, well, here's, x times y, etc. But if we don't know what that differential equation is, we can use a universal approximator to parameterize it, right? Because remember, a neural network is something that can represent any Rn to Rm function. So we can stick this in here and say there's some unknown Rm to Rm function that will complete this model, right? So it's a kind of, so this is a gray box model that is being handled with a neural network that is capturing unknown physics or unknown, biology, right? And what you can do is you can first train this neural network. It will learn the unknown relations for this model. And once you've done that, you can then do things like, you can pull this out and say, hey, if I do a sparse regression, right? So a sparse regression is essentially like a change of a function to a different basis, right? So once you do a sparse regression of this to say symbolic model, you can have it spit out, hey, this is the missing part of your model, right? And in fact, on this kind of example, like on Volterra, it'll tell you what you were missing from your model, and it actually will give you the LaTeX for, hey, from this amount of data, here's what you're missing from your model, here's how you'd write it in your paper, right? And if this could work in practice everywhere, then we would all be happy, right? We would all just take our model, what we know, we write down the simple physics, we would put our data in, and we would just get out the hard physics, automatically. So what we really see from this is that there are a lot of cases where it seems to be working quite well, right? So one of the properties for example, that you would not expect from machine learning methods is for them to very generalize well, right? If you train it on a small amount of data, it shouldn't go out to the future. But when you do it with this kind of method, it tends to have good extrapolatory values, right? And you can almost think about it as, well, if you think about Einstein's, theory of relativity and stuff, right? When we have these parsimonious if you have these parsimonious kinds of models, these kinds of scientific mechanistic models, and the mechanism is correct, then they tend to extrapolate well. And here, if we use the universal approximator and find mixing mechanisms, and those mechanisms are correct, it does tend to extrapolate well. And it's one thing to show that on toy problems, But it's another thing now that, a few years later, we've had the software out for a while. What we've seen is that people have taken this and, for example, taken it to black hole dynamics. You train it on a small amount of time, right? So this is the gravitational wave data from LIGO. And then you ask the question, if I extrapolate in the future with the dynamics that I've learned from the black hole, does it give an accurate model? The blue is on top of the orange. And so, this case worked almost as well as the kind of the toy data case. Where again, this is where you take some of the you take a model where some of the easy physics, right? You've written down like the first Taylor series approximation, and then you say, well, there's some nonlinear terms I'm missing. Put a universal function approximator on that. When you learn that from the data you have, you can extrapolate forward, right? So this is essentially a mixture of mechanistic modeling with deep learning. And I see a question on here where someone asked also random forests. So random forests are a universal function approximator, but they're not differentiable, which can make the training a lot harder. So generally, we don't use random forests, but there are ways to try to incorporate them, which is some of what we're doing in the near future. So yeah, that's a great question. So generally, when we're doing this, we're using differentiable types of models like neural networks or Fourier series and stuff like that. And I'll go into detail as to why that differentiability is required with our current set methods. So was it just one example, a toy example, and then one real world example that worked out like this? I kind of want to just like do the parade now and say like, oh, hey, look, it really isn't, right? Like, at this point, people are using this kind of software, right? And I think for that, for a statistics group, I think that's interesting because this shows that something is working, though, we will agree that we don't have any bounds on the generality and stuff. Right, so here, for example, is another case where we have, a physical model where the physical model on its own tends to have this divergence, if you can see these dots, whereas the physical model plus the neural network involved in there, it extrapolates in a way that is fairly good off of a very short training data. And this is for earthquake-safe buildings. Another example is, coming up with better models of battery degradation. Right, so there's a paper that shows that we can do this in a way that improves the prediction of battery degradation times by 19%. There's the construction of automated models for accelerated modeling and combustion. So, chemical reaction systems. What you can do is you can build the neural networks in a specific way. So that way you can only represent chemical reaction systems, so like mass action laws. So that way you've constrained it to a space that mechanistically has to be valid. And in this case, you get very similar results where small amounts of data can learn, and you can tend to learn models that seem to be working out well, right? Another case that's interesting from the literature here is also new propulsion devices. I'm not someone who knows much about propulsion devices. I pulled this out of our citation list, but you can see it follows the same thing, where here they have a partial differential equation, which has a neural network that is defining missing parts of the physics. They've learned the missing parts of the physics, and they're able to show in their paper that they're able to get very accurate predictions of how this new propulsion device is able to work, even just off of some very little data plus the extrapolation with the neural network, right? Here, another case where this all comes into play is in qubit preparation for quantum circuits, right? And I can keep on going through example after example after example, but what we can see now is we have hundreds of these citations of people doing this, like mixing the models with neural networks, and we see that it's working out well. And this kind of drove us to our next direction in the research, which was, well, how do we put some uncertainty quantification on this, right? How do you get an error bar on if when you're extrapolating, how do you learn whether you have put enough prior information that you can really know that this extrapolation works out, right? And so one of the directions that we went with this was probabilistic programming, right? It's a very quick jump, right, to kind of be able to say like, okay, you were doing optimization before, but instead of doing an optimization to be able to get the parameters which are most likely, instead let's get a distributional estimate for parameters, right? It's not that big of a jump. And what you can do then though is once you have a posterior for what are the most likely parameters of the model that would explain the system, right? That gives you a posterior over the weights of the neural networks embedded in the system, and you can sample them, right? So remember that process before where you have this neural network, and once you had the neural network, you could perform a symbolic regression. Well, once you have this, in this case where you have a Bayesian posterior over your, once you have a Bayesian posterior over your neural network weights, you can take samples from that posterior, and then you can ask the question, like, what percentage of the time does a symbolic regression give you a quadratic function? What percentage of the time does it give you a cubic function, right? And this can give you some kind of uncertainty quantification on the probability of missing certain mechanisms from your model. And so, one of the cases where we started really digging into this aspect of how predictive can these methods of scientific machine learning be was with epidemic models. We had a series of papers that kind of dove into different aspects of epidemic modeling with these kinds of methods. And so I think this is like a nice way of illustrating where the theory, not really the theory, but at least the empirics of robustness of scientific machine learning has gone. So one thing that we did here, this was actually fairly early in the pandemic, we looked at this idea of, well, you have the simplest model you can have of a pandemic is SIR, but if someone is quarantined, then they're not in the population. So here's an SIR with a quarantine term to be in a quarantine state where anyone that's in the quarantine state is not causing people to get infected, right? Very simple mechanistic extension, but the key here is that quarantine policies are different in every region of the world, right? And so we asked the question of if we do a semi-mechanistic model like this, and we have Q of t be some function, some universal approximator which we learn, do we actually learn something that is mechanistic, right? And a way to kind of to find that out is if you take this QSIR model and you train this neural network to give you a term that captures the quarantine, you can match that quarantine policy up against real data, right? You can go country to country to country and just ask what day was the quarantine actually imposed, and when does our model say that there should be an inflection quarantine policy? And you see that within days of each other, these things tend to align, right? And if you go to the supplemental of the paper, you'll see that the 100 countries or whatnot, where this is where it's great to have a graduate student go through all these different news articles and line them up. And what you see is that you do have a very nice alignment between where the model predicts that quarantine would occur and where quarantine occurred, right? And so, in some sense, when you create these mechanistic, these semi-mechanistic models, and then you try to map it back to the mechanism that you think it should be mapping to, at least there's some quantitative evidence that it is, at least in this case, doing something that corresponds to what you would expect. So what we started to do, though, was ask the question of, well, our hypothesis is that, scientific models are like information themselves. Like, we can replace data with a model, right? And so if scientific machine learning is to work like that, then we should be able to show this on simple cases, right? So we took some data where we, for example, we ran a 9-compartment SIR model. So we ran some giant simulation of an epidemic to give us data, and then we just asked the question of, okay, here is the QSAR. QSAR, remember, is this kind of semi-mechanistic with a neural network version of a extension of a epidemic model, and a neural ODE is just pure U prime equals neural network. Like, there's no mechanism involved. You just let the whole thing be a neural network that learns. And what you see is pretty striking, right? That, with the same amount of data, the thing that has epidemic kind of imposed into it is able to get much better predictions. There's actually something interesting in here as well that we noticed, in that the neural ODE, for example, like standard machine learning methods will not be able to impose laws that are true. So this is all normalized population, right? So this is percentage of the population that's infected, and a time series prediction method from a neural ODE can tell you that more than 100% of people are infected, right? Because it doesn't understand that everything needs to sum to 1. A neural network, if you put a neural network in the QSIR model, right, it's affecting a rate. That rate function is multiplied by I inside of these ODEs, and so you always have conservation of people. And so, for example, like if you want a deep learning method that is, giving you time series predictions that always imposes that the sum of all individuals in all states is equal to 1, this kind of QSIR model is presuming that, right? So there's a lot of structural information that's part of it, and you can see that given the same amount of data, it's able to give you much better predictions. So the structure information is correct, but also a lot of asymptotic information is correct, right? In terms of if you let an epidemic run sufficiently long, you will always have people end up in this recovered state if they can't go back to susceptible, right? And so you'll see that it always has to have a peak and has to go down. And so the scientific machine learning method at this point is effectively only having to learn where the peak is and how fast the drop off is. Whereas the neural ODE essentially has none of that prior information. And so we'll be releasing this study actually fairly soon on how graded amounts of model information being put into the system tends to give you more and more information, and better predictions. But I think that this actually leaves open a fairly interesting unanswered question, right? So, I'm using the term prior information and information from models very, very loosely because we don't have a nice way of saying like, the information content of the QSIR is 5 versus, neural ODE, which is, 1, and therefore it predicts better from data, right? We just kind of know this looks more epidemic than, proposing that it's just U prime equals neural network. And this tends to extrapolate better. This tends to learn from less data. That seems to be true. And right now we have these empirical results that we don't necessarily know how to quantify, how much prior knowledge model there is. So I think that's definitely one direction that this research all needs to go in. But one of the things that we went and did then was we looked at, for example, in the southern United States, right? We have this model that can tell us, when did people start quarantine and when did people react? And so what we did was we went to the southern United States, and in this other paper we asked, can we make counterfactual predictions, right? So essentially what we did was we took this QSIR model, right? And we used this to be able to learn the quarantine term. And then there was a time in the southern United States in the summer of 2020 where quarantine was effectively disabled. It was basically everyone was told you don't need to quarantine anymore, right? There was all these Trump rallies, et cetera, right? From which this all occurred. And so we can ask, first of all, the question is, is this model capturing something that looks realistic? If you go and you train this model on the U.S. southern states, what you'll find is that the quarantine policy or the predicted quarantine policy for this semi-mechanistic model, it has the quarantine policy as rising until some time point when it just suddenly drops off to basically a state of zero quarantine. And it turns out that the date at which that drop off happens is right next to where the actual quarantine, the stay-at-home orders expired, right? So once again, it kind of captures something that you would expect. If this was a purely mechanistic model, you would hope that these would be on the same day or nearly the same day, and you see that this really ends up being the case, right? And what we can do for a counterfactual in this case, right, is because we have something that is mechanistic-like, we could take this semi-mechanistic model and we can say, well, if quarantine wasn't, if the stay-at-home order did not expire, right, if quarantine was still in effect, then Q of t would be about the same. And so if we kept Q of t constant, then what would the difference in what our model predict be, right? We can then run that forward and we can see, here's how many people we would expect to be infected, and here's the number of people that were. And so we can use this kind of semi-mechanistic model as a way to be able to factor out, like, this is the amount that we believe should be due to the quarantine policy, right? And so we find this interesting because, we were doing this publication process, right? We were really looking at, can we, what we were really trying to solve here was, can we use this to be able to come up with, very quickly come up with a very effective, a way to be able to ascertain whether a policy is too restrictive or not, right? Because, how much, the question isn't whether we should do quarantine, it's how much quarantine should we be doing. And what we found through this is that we can use such semi-mechanistic models to start more making it much more quantitative. Like, okay, this is the true amount of case reduction that we should have had given these different quarantine policies. And so one of the things that we're kind of doing as a follow-up is, over a larger epidemic, you can look at different levels of quarantine policies, right? You can then discover these through the semi-mechanistic model, and then you can use that to be able to say, like, oh, at this time point, people had a policy like this. At this time point, people had a policy like this. And so how much risk is involved in just, removing, masks from indoors and whatnot, right? And you can start to try to pull this kind of more detailed information out of larger context. So this epidemic section is mostly to kind of show what are some ways that we've used scientific machine learning. Though, as I showed earlier, there's many different other contexts, from physical models and chemical modeling and such, where this is being used as well. Though I think that some of the social aspects, like epidemics and some of the social psychology ones, are very interesting, because these are the cases where we have the least predictive, quantitative models, and this is one way that we're finding helpful for coming up with those models. Another case that I want to highlight really quickly before moving to the software and math kind of portion is nonlinear mixed effects modeling, because nonlinear mixed effects modeling is one of these core statistical areas that people have looked at for a long time. And what we really were looking at, though, was that with one of the issues in nonlinear mixed effects modeling is actually the development of the components of the model. And so looking at this in the case of pharmacology, if you don't know what a nonlinear mixed effects model is, let me kind of break it down into the pieces, right? So you have a covariate model, which is, when someone first walks in the clinic, this is the information that you can get about them instantly. So for example, their weight or their sex, right? This usually goes into a structural model, which the output of the structural model is the parameters of a differential equation, which gives you the dynamics of something, right? So generally, nonlinear effects can have any nonlinear function as the last component here, though generally what we see is that most use cases are using some kind of differential equation for that nonlinear function. And so what is interesting, so the way that this is used in the clinic and such is that if you can learn the fixed effects, which are basically the average effect of weight or the average effect of sex, right? If you can learn these effects, then you can know when someone walks in the clinic, how are they on, from this information, how are they different from just the pure average person, which will make it, how they will react to a drug differently. And you can use this to be able to come up with more personalized dosing strategies, right? So you can say, well, if someone is above this weight, then they would have, take 2 doses versus, below this weight, they should take 1. And you can have a very prescriptive model of how the drug dynamics will go based on these predictive factors, right? And so the really interesting thing about nonlinear mixed effects modeling is that it has to solve a fairly difficult maximum likelihood procedure, right? So, if you know NLME, is this problem of finding the fixed effects and random effects such that the expected value of the random effects is 0. The reason is because the random effects are thought of as a fudge factor, and so you want to say, okay, on average they have 0 effect, and so given that on average the random effects have 0 effect, what would the fixed, or given that on average the random effects have 0 effect, what would the fixed effects or the average effect be, right? And so the interesting thing with this, though, is that this model right here, you should probably look at it and say, well, who came up with that thing, right? That's really the big issue, right? So we've been working, for example, a lot of the Julia tools that we've been working with have been used, for example, by groups like at Moderna, and where we've really looked after accelerating the standard nonlinear mixed effects compute. What we've really been looking at is how do you improve the model development process, right? Because that's where most, the people who are in pharmacometrics, where they're spending their time day to day is actually developing these models. So if you actually want to make the drug development process go faster, you can keep on improving the compute, but at some point, the bottleneck is just the time it takes for a human to come up with these factors, right? And now the interesting thing here is that in general, you go, well, deep learning can solve problems from data, but how do you make deep learning solve a problem that has to have a random effect with respect to zero, except like all these little constraints make this a fairly difficult problem. But if you stick the neural networks within these problems, right? If you say subject to the constraints of a partially known dynamical system with a statistical model, and if you make the weights of your neural networks be the fixed effects of this model, it turns out that you can do everything that you would have done before with the nonlinear mixed effects model, except now what you'll learn is an average, the neural network for the average person, right? And if you know the neural network for the average person, this gives you the average perturbed dose from the covariates. And once you do that as well, you no longer have to screen the covariates for things of which you know how to model. You can have the covariate matrix be, you take someone's genome and you slab it through a neural network and say, find for me which of these factors are predictive. That itself, you can then run a symbolic regression to ask the question of, okay, what terms did the neural network use? What terms did it not use? To be able to then learn which of the factors are predictive of the dose dynamics and which of them are not predictive. And so we've actually gotten this all the way pretty close to the clinic at this point, right? So here's actual code where you can specify like, oh, my parameters are from a neural domain, and I can define these pre-functions with neural networks. And so if you want to learn more details on the nonlinear mixed effects case, there's actually a talk on the you can search for Deep NLME. There's a talk at SciMLCon 2020, which is just a month ago, which goes into the case studies about how this was able to learn models that would be able to be predictive of different dosing strategies on new patients. But I'll skip over the rest of the details there to get into some of the more mathematical pieces. Right? But please check out that video if you're interested there. Yeah, so here making the transition, right? Another way that you can use scientific machine learning is for coming up with what's known as surrogate models, right? So what is a surrogate model? I think it's easiest explained by an example. So here is a three-dimensional Navier-Stokes simulation, right? So it's a Boston-esque approximated Navier-Stokes of an ocean column that's used in a climate model. And so, the real question is, well, when we have a climate model, we don't need the whole three-dimensional case, right? All that we really need is a one-dimensional approximate. So how can we build a model of just the z-axis for heat flow in the ocean if we have the physics for a three-dimensional model, right? And that actually is a classic question that people have been asking with statistical models. And so what you can do is you can take an integral in the xy plane, and if you expand it, the first term in the Taylor series that you get is everything except this neural network, right? And so what we've done is we say, okay, what we can do is we can do the first term approximation that you would do in a standard climate model, but we can add a correction term and say, well, there's more corrections than just the first term, right? So there'd be a summation of all the extra terms, and that's what we can capture in a neural network, right? And so now what we want to do with this is if we want to learn a PDE that is just the one-dimensional PDE of how heat flows up and down, right? What we can do is we can take the heat flux at every single point, and that's data, right? So we can take data from our three-dimensional model, and we can say what happens in the three-dimensional model on average over x and y has to be true about our one-dimensional model along z, right? So you can take your heat flux data, right, and you can say this neural network has to capture everything that's not captured by this term in the heat flux. So you can just directly say, I need to get my heat fluxes correct. And if you do this is, if you take so Oceananigans is one of these three-dimensional Boston-esque approximated Navier-Stokes simulators. NDE, this is the neural differential equation with the neural network in here, where we've trained it against the heat flux data. And you can see that you tend to get a divergence over time, right? So scientific machine learning is bunk and nothing works, right? Now, right, so let's take a step back though to kind of look at what happened there, right? So I said, okay, we have this three-dimensional case, and we want to turn it into a one-dimensional case. And in the one-dimensional case, the physics says that this is a good approximate model. Slap a neural network in there for extra terms. For the neural network, we train the neural network against the data on the missing derivative information, and over time we get a drift. right? And so we've controlled the derivative to be correct, sans numerical error, and we get something that drifts over time. And so, if I was talking to a control engineer, they would instantly walk to you and say, well, you controlled the derivative. Of course you got drift over time. You have to control the integral if you don't want to have drift, right? And so what if we do that, right? So instead of taking the flux information, instead of taking the heat flux or the derivative at each time point and matching that to the neural network, what if we solve the differential equation with a given neural network and then check the loss of the solution against the three-dimensional solution against the solution with the neural network, right? So now instead of looking at the loss function in the derivative sense, we're looking at the loss function in the solution sense, right, on the solution of the differential equation. And when you do that, you get estimates which are radically better. Like, actually, this ends up being the best closure method that we came up with. So we'll be publishing this fairly soon. And this is one of the methods that we'll be using within the clean climate model. So this is really the key, though, that if you want to do this correctly, you cannot just necessarily, take your data, train it in a neural network separately, and then slap the trained neural network into the simulator. That tends to give you all sorts of numerical issues because you're not necessarily you're getting the derivatives correct. You're not necessarily getting the solution correct, which can cause drift over time. If, for example, the derivative is always slightly negative, then you'll have a compounding error, right? Whereas if you try to make sure that the integrals are correct, you get different results, and those results tend to be much more stable. Which means that you cannot train your neural network separately when you do this, right? You cannot do scientific machine learning where you train a neural network on data and then put it into a simulator. The simulator needs to be part of that backpropagation process. So however you're doing that training needs to have the simulators in there. And so that becomes the major question, right? How do you fit a neural network inside of a simulator? It turns out that there's tons of different ways of doing this. They're all called the adjoint method, but the different adjoint methods that you can do all have major differences in the memory scaling and the compute performance. And so I kind of want to go through a little bit of a discussion to show you where all these different adjoints come from, right? Because many people here might have gone through, like, oh, here's how you do the adjoint of an ODE, or here's how you do the adjoint of PDE. But I want to highlight the computational aspects that get involved. Right, so let me do a quick derivation here, right? So let's let u prime equals f of upt. This is our ODE, and we want to take the derivative of a cost function with respect to parameters. So our cost function will be this capital G, which is some cost function that is an integral over the instantaneous cost function. So, there's a cost at every instantaneous time point, say, the difference against your data set at, time t. You add up all of your differences against data at every time point, and that's how you get your total cost, right? And I want to take the derivative of the total cost with respect to parameters, so that way I can do gradient descent on this bad boy right here and make my loss go to 0, right? So how do I do that? It turns out that every adjoint derivation has kind of the same trick. The trick is that you introduce a Lagrange multiplier here and you subtract off 0, right? So why is this 0? U prime equals f of upt. This is the definition of the ODE. And so this is 0 right here, right? So we had 0. We take the derivative with respect to p. And so this is, by the chain rule, you get this whole thing here. Now, the issue is that we need to do a bit of integration by parts. So we do some integration by parsing around, and I have a YouTube video that goes through this in much more detail. And so I point to the 18.3-7 scientific computing and parallel computing, or scientific machine learning and parallel computing course at MIT. There's a whole YouTube video that walks through this over a 2-hour period. So I'll give you the highlights. But once you have the version and chain rules, we want this to be in terms of S everywhere instead of S prime. And so how do you turn a derivative into a non-derivative term? You use integration by parts, and then after you do a bunch of integration by parts, you realize that you can simplify this expression if you make lambda equal to a very specific thing, right? Because if you define lambda such that this term is 0 and this term is 0, then you're golden, right? Then your adjoint equation is much easier to use. And that really then becomes the key. So you define lambda. So lambda is defined by a differential equation that forces one of the integrals to be 0, because then it makes the rest of your calculations easier. So what do we do? So we define lambda to be this, and that makes our adjoint method be equal to this, right? So what are the steps of actually getting the derivative of an ODE solution with respect to parameters, right? A quick summary of what we did there. What you do is you would solve this differential equation. U prime goes forwards, right? Then what you would do is you would solve this lambda prime in reverse. The reason why is because if lambda of t equals 0, it makes one of these terms simplify to 0. And so you choose that. And you also want this lambda to solve this differential equation, so that way this is 0. And so you first solve u going forward, so this is one differential equation. You solve this differential equation going backwards. And then once you have u of t, right, you have this continuous function, then you can take this integral and ta-da, you get the derivative of the cost function with respect to parameters. And while this derivation might look foreign, if you've ever done, for example, derivatives or backpropagation of a recurrent neural network, this should actually look very familiar, because what I'm saying is we have some differential equation. You solve this differential equation forwards. You solve some differential equation backwards, and it's a very specific one I'll mention in a second. Right, so you solve a differential equation forwards, and then to get the derivative, you solve a differential equation backwards, and then that gives you essentially the derivative with respect to parameters. So this is almost in some sense continuous backpropagation. It's not even almost. I'll get to that in a second. But there's some details in here, right? When we write this down at a very high level, we're missing the computational details. And so when I say you solve this lambda equation backwards, one detail that's in here is that you have to take the derivative of that ODE function f with respect to u at given time points. And so how do you actually know what u of t is in order to take a derivative, right? Because we solve this as a separate differential equation. There are three ways you can do this. In fact, there's probably even more, right? So one way you can do this is that you can solve you can take any differential equation and try to solve it in reverse. This would give you a way of getting u prime at each time. If you solve this equation simultaneously to the lambda equation, then you would always have u of t, and you can define this. The other thing that you could do is you can store the entirety of u of t going forwards. Of course, that's going to give you the correct value of u of t of all times, but that will cost you memory. Or you can do something called checkpointing, which is you only save u of t at specific time points, but whenever you need u of t in an interval, you resolve that interval. So more compute versus less memory. Now, I'm going to quickly go over some of these different aspects here. So, for example, in this equation for the adjoint equation, right? This is the Jacobian transpose multiplied by a vector. It turns out that's the primitive of reverse mode, and that's what I mean. Like when you do this process, you go forwards, and then the way that you define the ODE that you solve backwards is the reverse mode of the ODE equation. So so it really is a continuous form of reverse mode. Automatic differentiation. But the key here though is that when you can do this by using what's known as a vector Jacobian product, or you can do this without ever calculating the full Jacobian if you have reverse mode primitives available to you. And that's a trick that people use in reverse mode automatic differentiation literature, which means that even when I write down this lambda equation, there's many different ways to compute this, where computing the full Jacobian with numerical differentiation or something is very, very, very suboptimal in comparison to any of the reverse mode based approaches. But each of the reverse mode based approaches, right, have all the trade-offs of reverse mode AD. So some will be better when you have GPU, some will be better when you have operations that are nonlinear in all sorts of different cases. Now, and the last thing is that when I said, oh, you get lambda of t and then you compute this integral. Well, what do you do to compute this integral? Do you store the entirety of lambda of t, or do you append it as an ODE to your other equations? Because if you append this as an ODE to your other set of equations, then you don't have to store it in memory. So I just gave you actually like a whole list of if you take different combinations of these choices, you get the different 20 methods of adjoints in the literature. But it really just comes down to these different choices. And are all of these choices good ones, right? So here, for example, is the normal ordinary differential equations paper, which if you look at this, right, what it does here is it solves forwards, it solves this one backwards. How does it make the choice here? well, it does the choice by doing the U prime backwards, and here it does a reverse mode AD with the vector mode, and here it does the integral by appending the ODE, right? So every adjoint method really just comes down to be a choice of these different aspects. Now, is that a good choice or a bad choice, right? This ends up being the least memory costly choice, but also if you try to do this reversing process, you can show that it's unconditionally unstable on a lot of cases, such as on partial differential equations, because it turns out that even though you can reverse any ODE, you cannot necessarily numerically reverse any ODE in a way that is numerically stable. So that's another aspect to think about, right? So if for example, if you take U prime equals lambda U, you solve it forwards, and then you solve it in reverse, how much error how much error against your original condition did you actually get? It turns out that as lambda goes to minus infinity, right, you get exponential growth in the amount of error in that process. And so naively reversing is not necessarily a good thing to do unless you have a small bound on the Lipschitz constant of your ODE. I'm going to be running up against time here, but basically what I'm saying is that when we say that you're taking the derivative of an ODE solution with respect to parameters because you're putting neural networks inside of differential equation solvers, this question of, oh, you use an adjoint method, right? There is an answer to it. People have done adjoints for years, but there tends to be, there isn't just one thing that is an adjoint method. There's there's the combination of all these different choices in there that are required to be able to get an adjoint that is fast and that is stable for a given problem. And so what we've really tried to do with software then is we try to make it so that way getting the most memory efficient and the most compute efficient adjoint, it would be as easy as stiff ODE solvers, right? These days people don't think about how difficult a stiff ODE solver is. You just use ODE 15S or something, whenever it comes up. And so what we've done really is we've automated this process of finding stable adjoints and choosing the most compute efficient forms. And so if you look at all the different cases, you'll see that, some of the cases that are used throughout the literature a lot, if you use them with the stiff ODE solver, you actually get cubic scaling with respect to the parameter. So, you get cubic scaling with the number of weights in your neural network, which is extremely bad compute performance, but you can remove that compute issue by using a bit more memory, right? So, if you have more memory, you should use it to drop the amount of compute. Otherwise, you should use less memory, but, more compute. And there's this whole trade-off matrix that comes from, the different choices you can make in there. I think one issue that I also want to describe in here is that you also have to come up with very specific adjoint methods whenever the system you're looking at is chaotic. So, for example, on fluid dynamical systems, right? So if you put a neural network inside of a turbulent fluid dynamic system and you take a derivative, well, that you get exponential growth in the error of your simulator as you compute forwards. And so why do you think that your derivative is not going to have exponential error? It turns out that the Lyapunov exponent is the rate at which your derivative explodes. And so you can actually show that automatic differentiation will give you essentially an infinite answer. That's kind of the definition of your tangent space exploding. And so you have to come up with completely different methods for calculating adjoints in the case where you have chaotic systems, right? So doing scientific machine learning then means you have to start going to all these different cases where you say, okay, I have good conditioning numbers on my Jacobian, bad conditioning numbers on my Jacobian. I have chaotic systems, non-chaotic systems. All these different cases can require different ways that you calculate the derivatives. But if you can calculate those derivatives correctly, then you can learn neural networks within your scientific simulators and use all of the techniques. So then we showed, for example, that we're able to get about 3 orders of magnitude faster by really optimizing, these techniques on, for example, stiff partial differential equations. And so these are not small optimizations. We're talking, 1,000 times faster by changing these methods up. And so, I think that one last thing I wanted to mention before we get to questions is this whole question of, you'll see a lot of other methods out there in scientific machine learning. So why is differentiable simulation one that is interesting, right? And the real, come back to this question of, it really is this property of not just using knowledge about physical models, but also using the knowledge of numerical analysis. right? So for example, physics-informed neural network is a purely neural network approach that doesn't have ODE solvers in there, that uses the neural network to solve the ODE, right? But what you can see is that if you run that kind of technique to be able to, for example, give you parameter estimation of the Lorentz equation system, it's about 1,000 times slower than using, say, a differentiable simulator. And I think that this is something that we kind of seen works across a lot of different cases. So, for example, we took another paper that's all about how, here's a method that claims to be much faster than a lot of classical numerical solvers. And so, they show that their numerical solver on this equation takes about this long, whereas, this neural network approach takes about this long. But if you use an optimized numerical solver, you see that it actually is so fast it's not even on the chart, right? And I think that I want to leave with one word of wisdom here, which is really that, these kinds of results that out there, right? You'll see a lot of things about how Fourier neural operators beat classical solvers and all these other different things, right? Generally, what you'll see though is that they're not using very optimized classical numerical methods. And what we found is that if you can greatly outperform these neural network methods if you use really optimized classical numerical methods. And so what really seems to be the case out there is that, machine learning, really what it is it's machine learning's true use case is a productivity growth, right? I mean, using the machine learning frameworks are very easy to use optimally. And so, it's very easy to get a deep ONet that is fairly close to optimal, right? The first code that you write down in PyTorch should be fairly optimized. Whereas for classical numerical solvers, it's just not the case. You need to worry about a lot of computational details, like writing down your Jacobian using mutation and all these kinds of extra aspects. But it can be optimized a lot more than the machine learning approaches. And so I would be very careful when looking at a lot of the results in there. This is not due to any issue of the researchers themselves. It's just that it's harder to optimize classical numerical codes. And as I mentioned, with the adjoint methods, there's not just one, but there's like 20 of them. And so if you use the wrong one, your performance can be off by a few thousands. And so, so really what I want to mention here is that, making these classical numerical methods work well with machine learning is a very difficult process that will take a long time, and it will take a lot of software engineering. Though what we see from it, at least already what we see, is that it seems to be the approach which will be much more computationally efficient, because it's essentially encoding all the information that we have of not just deep learning and physical models, but also about numerical methods like Runge-Kutta methods and all that. And so how much that information will help is still something that remains to be seen, but we can go case by case and see that, really optimizing classical numerical solvers and mixing them with neural networks seems to be a very computationally efficient approach. So that's what we have in the SciML open source software organization. You can check us out online, but I think I've gone a little bit over the time I wanted to go, so I'll go straight to the questions now.
Thank you, Chris, for a wonderful talk. Any questions from audience? I see a question from Q&A. This is a question about the COVID infection model you presented. Can these models account for seasonality or infection rates for different variants?
Wait, say that again?
So this is a question about the COVID infection model you presented. The question is, can these models account for seasonality or infection rates for different variants of the virus?
Yeah, I mean, so if you take this model, right, you can, if you encode more mechanism into it, right, the way that you encode more mechanism into this kind of model is you'd normally take a cross product between the SIR model and different infection rates, right, and that would give you different infections of different strains, right? So if you do the standard thing that you would do in epidemiology, essentially that's kind of the case, right? So you do the standard thing that you do in epidemiology, right? You create the most mechanistic model that you can. The places where you have uncertainty about how something is acting, or if you want to understand, how quarantine rates can be differing between these different parts, you can put in these neural networks to capture those unknowns, right? So yeah, I would say that, if you can make that kind of mechanism in your standard mechanistic model, then you would just do the same exact process here. Really, what we're doing is we're adding neural networks to mechanistic models. And I guess another thing to kind of be aware of is you don't need to have just one neural network inside of your process. You can train them simultaneously. And we've shown that, for example, here, where here this is something we call the graphical UDE, where it's encoding essentially no information about the epidemic except for the graphical information. So, for example, S can go to I could go to R, and I could go to D, but D cannot go to S, right? So this has this kind of graphical information in here. And what you can see is that you can train these neural networks simultaneously and then do sparse regressions and learn them, right? So you can write out a full mechanistic model and say, oh, I have an uncertainty here, I have an uncertainty here, I have an uncertainty here, and capture each of those with universal approximators, right? Neural networks or Fourier series or any of these approximators.
Great. Yeah, I actually have a related question, and because in statistics we have those semi-parametric models. I'm sure you probably aware of. I think the idea is related to the scientific machine learning you present, but of course your method is a universal tool for, in some sense, fitting very flexible semi-parametric models. So the idea is, for the part and you know the science behind it, you use parametric models, and for the part I guess you don't know much about, you can use a very non-parametric form. And I want to perhaps to comment on this, and do you see a connection?
Yeah, there definitely is a connection, right? Now, in a lot of the cases in statistics, though, right, a lot of those cases, right, you kind of work with a non-parametric model in a sense where you can derive some estimators and such, right? In this case, what we've really done is we said, okay, we care a bit more about trying to get the correct nonlinear model than trying to learn every detail of it for now, right? I think that there's a lot of details we need to learn about the uncertainty quantification, but so what we can do is we can specify a fully nonlinear model in like the most difficult case we can think of, right? You can make it a stochastic partial differential equation and then stick a neural network in there. And as long as you can train that neural network in that context, you can use it for the semi-parametric form, right? And I think that what illustrates this nicely is the nonlinear mixed effects case, right? Because, and that's why I like to bring this one up, where it's like, nonlinear mixed effects is one of these statistical cases where it's a maximum likelihood estimation with respect to some of the parameters, with other ones having to do an expected value, right? And now, really trying to derive a non-parametric model for this case would be extremely difficult. It's really hard to really even sit down and start to try to do that, right? Especially when you have the non-linearities of the dynamical system, right? But it's fairly straightforward to say, okay, a version of a non-parametric model is I have a neural network for some things. If those neural network weights are fixed effects, then I can do a maximum likelihood. I would do a maximum likelihood derivation for the neural network weights, and as long as I can calculate the Hessian of this system with respect to the neural network weights, then I can optimize it, right? And so it's basically throwing aside and saying, well, I could do all of my semi-parametric models in a fully nonlinear case with very specific maximum likelihood estimations, as long as I can just calculate derivatives. If I can calculate derivatives, then I can do this. Yeah. You lose a lot of the factors, like you don't necessarily have good uncertainty quantification on this, and so there's a lot more that we need to do in terms of like, okay, how do you do Bayesian methods on this effectively, right? But what you can do is you can use this approach to basically take any parametric model and turn it into a non-parametric one, and keep the same maximum likelihood, or keep the same objective there as well. And so that's where I think it's interesting, right? Because it basically says there's no limitation to where you can use it, though anytime that you do use more neural network neatness, right? Any more deep learning you get, the less good extrapolation properties you have. And so the trade-off is more in terms of the trade-off ends up in more in terms of like, you want to use as much parametricness as possible, or maybe not make it overly nonlinear, because then you have way too many parameters and whatnot.
Yeah. But
you can always go to a less parametric case.
Yeah, thank you very much. Yeah, this is indeed very flexible universal framework. Yeah, there's another question, how the methods are related to causal inference in terms of answering counterfactual questions and learning structural models.
Yeah, so Yeah, so that's a great question. Yeah, so I mean, one of the ways that we really look at this in terms of causal learning, right, is that if you learn a neural network, say in a differential equation, like if you can turn that neural network back into mechanism, then that actually gives you a causal model, right? Someone who does ecological modeling would look at the log-Volterra equations and say, this term right here means that rabbits are interacting with wolves, right? And like not only is it causal modeling, like it's telling you this is what's causing the changes, but it's also telling you that this is the mechanism by which the change is occurring, right? And so really where this can kind of help is that this kind of gives you an idea of, well, I can do causal modeling where I presuppose some mechanistic factors and I try to learn what the other factors are. And once again, the nonlinear mixed effects case is kind of an extreme example of this, where in this case, for example, if you want to do causal learning and you want to understand, like does sex actually cause differences in the dynamics of this drug, right? One way that you can do this is you can have a neural network be the structural model. You then learn this, you just train this neural network and you train your dynamical system, right, to be able to learn these neural networks. You then do a sparse regression or a symbolic regression to learn the symbolic model. And what you'd hope for is either yes or no, this has a term in there that is related to sex, right? And that would then tell you whether the clearance of the drug or the volume of the drug body, right, whether those are actually related to the sex covariate, right? And so this can let you learn causal models deep within different kinds of scientific models. And actually, there's a case from talks that I was giving about a year ago where this showed up, where we did this on epidemic models and we threw some extra terms in there just in case. So we said, like, I think it was something like, we allowed the neural networks, we allowed neural networks in this kind of model discovery case. So that way these neural networks can take in, they don't just take in S and I, they take in SIRD. And then when we do the symbolic regression, it says, yeah, no, the rate at which people go from susceptible to infected is not dependent on the number of people who died, right? It's dependent just on the number of people who are currently infected, right? And so, it's able to give you these kinds of information when you do the symbolic regression, because it will basically cut out the factors that are not predictive. We've seen that this works in a lot of cases, though. Again, I cannot specify, like, oh, with this amount of data or with this amount of prior modelness, right? You will get the correct causal model out. What we've been able to show empirically is that as you have more data and as you have more prior model, you need less data to be able to do this effectively. Though there is, that is still a very fuzzy thing on, like, oh, you just need enough data for this to work, right? And we know that, the next frontier will really be about, trying to quantify, like, with this information, I can do it effectively. So.
That makes sense. So let's see whether we have more questions. I don't see any from the Q&A. I think we are right on time. Perhaps it's time to conclude today's talk. Chris, thank you so much. And we will post the video online, and many more people will see your great talk. Thank you so much.
Yeah. Thank you very much.
Take care.
You too.